All right, welcome back. This is Kinetics Part 3. We're going to talk about half-life real quick for first and second order reactions and sort of go through a little math to kind of show you how they work. So what are we talking about when we say half-life? So half-life would be the idea of what is the time at which half the concentration has changed. So if you started with some initial concentration, let's say you started with 4 molar, time's going to expire, and eventually that initial concentration is going to go down to 2 molar. So that's exactly half. So time half, and so we use this right here. So what is the half-life? So what is the amount of time it takes it to reduce its concentration by half? And so another way to write this is you could say the time equals 1/2 the starting concentration. That would kind of be a more official way than this. I don't want that. Okay, so let's go ahead and take and just sort of work through the integrated rate law. So the integrated rate law is the natural log of the concentration at a given time equals negative slope times time, let's see, plus the natural log of the concentration at the initial starting point. Okay, so this is our integrated rate law. This doesn't look good, so I'm going to fix that. And it doesn't really look much better, does it? Okay, just ignore it. That's what I'm going to do. Okay, so if I take this, I can derive this equation from it. So I could say the natural log of the concentration at the starting point divided by the concentration at the time equals the slope times the time. And so this would just be a way to morph your original equation, or to derive your original equation down into this. So what we want to know is this. We want to know at what point, let's say, let's throw some values in here. So at what point would this value, if we initially started with 1, then half of that is 1/2. So what we want to know is, if we started with 1 molar here, what's the time it would take for this to go down to half molar, or we could write 0.5. And so if we wrote that out, we could say, well then, what is the natural log of 1 divided by 1/2? So we're inserting the values in here for initial concentration of 1, and then we want to get that down to half. And that's going to equal k, and we want to know the time. So this is kind of what we're solving for right here. Okay, so 1 divided by 1/2, we might as well just say 2. So what we have is the natural log of 2. Okay, 1 divided by 1/2 is 2, and so the natural log of 2 equals the slope times the time. And so the natural log of 2 is 0.693, and so 693 equals kt. And so just to sort of get it so that time is on one side and these other things are on the other side, we could say the time, and let's say sub 1/2, so we say that's half time, is going to equal 0.693 divided by the constant. And so that's the equation for half-life for a first order reaction. And so because first order has a direct relationship, if you double the concentration, it doubles the rate. Because of that, it always takes the same amount of time to reach a half. And so it really makes it so that the initial concentration doesn't really matter. All you need to do is get to half of whatever it is. And so it's going to just always be this number divided by the constant. One of the things that you might notice is that that sounds very similar to how radioactive decay works. And in the case of radioactive decay and nucleuses falling apart, they always tend to follow a first-order reaction half-life. And so as far as we know, all radioactive decay is first-order. But in equations, sometimes we have second order. So let's look at second order half-life. So in the case of half-life for second order, it's not quite as easy because the initial concentration is going to matter because the lower the starting concentration, basically the longer the life, because the concentration gets affected by a power of 2. So it goes like this. So it's 1 over the starting conditions. And so then this would be the equation that you would use for half-life for a second order. And so it depends on the concentration of the reactant, so it changes the time interval as the reaction progresses. So as the reaction progresses, that time interval isn't exactly the same as it is in a first order. So the time interval will get longer and longer and longer as the concentration decreases. Okay, so that shows you a second order half-life equation, and you could plug numbers into that and solve for that, and also shows you a first order half-life equation. Where'd it go? There it is, right down there. This is first order, and you could use those accordingly to plug numbers into them and to solve for half-life.